From the previous video, we learned about backpropagation and fundamentals of neural networks. In this video, we'll begin exploring Keras and TensorFlow. Keras is a high-level API for TensorFlow that simplifies building and training the neural networks. It shares many similarities with PyTorch. Learning Keras helps you build a strong foundation in deep learning. In the future, transitioning to PyTorch library will be easier if you're already familiar with Keras. Here is an overview of this video. Keras APIs are pretty self-explanatory. We are directly working on practical examples, using Sequential API to build a neural network and classify fashion MNIST dataset. This dataset contains pixel images for clothes, shoes, etc. Second example, we will use the Sequential API to predict California housing dataset. In Chapter 2, we use the linear regression. Now we are going to try it on a neural network. First, load data and separate them to training, validation, and test sets. Neural networks generally perform better when input is in between 0 and 1 or -1 and 1. We can normalize data by dividing 255 and load the first 40 samples into the notebook. This example looks like images below. Fix this random number as 42 in TensorFlow so that we can reproduce the same result in different executions. This is a Sequential API. The first layer is a flattened layer. It converts our input data 28 by 28 matrix into a one-dimensional matrix so that inputs can be processed by the hidden layers. Next is a dense layer with 300 neurons and following another dense layer with 100 neurons. They are all use the ReLU activation function. ReLU activation function prevents gradient vanishing and exploding. We will dive into the gradient vanishing and exploding in the future videos. For now, we will just use it. The final layer is using the softmax activation function. The final output will become 10 different probabilities. They add up equals to 1. Each number represents the probability of a particular class. At this point, we have set up the structure of the neural network. The summary method shows the structure details of a neural network. As you can see, the first dense layer contains lots of parameters. 784 times 300 plus another 300 bias term for each neuron. Other layers' parameter can be calculated as the same way. We can print the parameters in the first hidden layer. Weights can be randomly initialized and the bias are initialized as 0. Now we compile the model using the sparse categorical cross-entropy function as a loss function. When the target label is an integer representation of the class, we need to use a sparse categorical cross-entropy. When the label is a one-hot representation, we need to use a categorical cross-entropy class. The SGD optimizer will train the model using stochastic gradient descent. It applies the backpropagation algorithm as we described in the previous video. The default learning rate is 0.01, and we use accuracy metrics to measure classifier performance. Now we feed the model into the training dataset. Each epoch processes all the training data. In our case, we have 55,000 images in the training set. The larger epoch, the longer time to train and might overfit the model. The batch size default is 32. Use 55,000 divided by 32 gives us 1,719 forward and backward propagation in each epoch. We pass the validation data to measure the performance of the model at the end of each epoch. As we can see, Keras shows a very detailed explanation of each epoch. At each step, training validation accuracy is improved and loss is reduced. You might have noticed that the first few validation set accuracy is better than the training set accuracy. This is due to the calculation. Training accuracy is computed as mean over total training error during an epoch. There are 1,719 iterations for each epoch. They will sum up all the training errors in each iteration and divide 1,719 to get the training error. The validation accuracy is calculated at the end of each epoch. We can draw all the history data points on a graph for better visualization. The validation loss is still going down, so we should increase the epoch parameter. At a certain point, the validation loss slightly goes up. It indicates the model starts to overfit. In order to achieve the better results, we can tune other hyperparameters such as batch size, learning rate, etc. Now we have trained our classification model. We can use it to predict the first 3 test sets. You can see our model is not fully sure about the first testing data, but very sure about the other 2. We can use the Evaluate API to evaluate our model on a testing set. This number looks pretty good. Now, move to the regression task. Let's use a neural network to predict the California housing dataset. Keras provides a pre-processing layer, which helps shift and scale the inputs. It works similar to the standard scaler. After this normalization layer, the dataset is centered around 0 with standard deviation of 1. Different from classification neural networks, we use MSE as a loss function for training and the root mean square error to measure performance. We don't need to put any activation function, so the model can output any numbers. As for the test set model evaluation, the RMSE is 0.53. If you remember the RMSE result from my previous video, it is better than a linear regression, but worse than a random forest. This is the end of this video. I hope you have a first impression of Keras and learned the Sequential API. If you have any questions, please leave the comment below. Please consider like and subscribe, and I will see you in the next video.